Welcome! In our lesson today on acid-base chemistry, we're going to be practicing two different skills, writing molecular equations and net ionic equations, where water is a driving force for acid-base neutralization, and when gases evolve for acid-base neutralization. We've practiced in a previous lesson the precipitation driving force for a double replacement. These patterns are again double replacement, however we'll have a water or a gas molecule as our driving force. We're being asked to consider the following bases as we move across, reacting with the following acids as we go down. So acid-base chemistry. And what we're just going to write in the boxes that are provided here is the driving force, either the word water or the term gas. We'll write the molecular equation, but I will be hopping over the complete ionic and go directly to the net ionic equation. That's a skill we're most likely ready for. Let's begin by writing out our formulas for each of the acids and bases, and I'll just start by going across. We have potassium hydroxide, KOH. Calcium hydroxide, CaOH taken twice based on charge. We have sodium hydroxide, sodium hydrogen carbonate, NaHCO3, sodium sulfide, Na2S. Technically, we have a base for KOH, ends with an OH. We have a base, ends with an OH. This is a base, we have an OH. But sodium hydrogen carbonate is classified as a salt. It is an ionic compound built of a positive and a negative ion. Same is true here. Na2S would also be considered a salt. Here we have hydrochloric acid, HCl, acetic acid, HC2H3O2, and sulfuric acid, H2SO4. Note to self, just as we remind ourselves, this acetic acid is weak. Sulfuric acid and hydrochloric acid are both strong. That will make a very important difference when we think about writing out our molecular and our net ionic equations. We're working to memorize the 7 strong acids so that we also know the weak. The bases and the salts are all water soluble. The strong, weak, and strong over here, of course, are acidic, and so they are also aqueous. So our adjectives will always be AQ on the left side of our arrow. Let's begin modeling for letter A. I'll start by writing hydrochloric acid, AQ, so that's aqueous. It's going to react with potassium hydroxide. Add the adjective, AQ. Simple double displacement, we have +1, -1 all the way through, so we're going to form HOH, which we can write as water, and KCl. Of course, the adjective on water is an L. It's a liquid molecule. KCl is a water-soluble salt. It is aqueous. We know to dissociate the strong electrolytes. HCl is a strong electrolyte. It will dissociate H positive ions and Cl negative ions. KOH is a strong electrolyte. It will dissociate into positive potassium ions and negative hydroxide ions. Pure water is a non-electrolyte. It stays together since it is a molecular compound. And KCl is a strong electrolyte. It will dissociate into potassium ions and chloride ions. Do you notice the spectators? The spectators end up being chloride and the potassium. So when I write out my net ionic equation, and I'll do that in the space provided over here, we have aqueous ion of hydrogen combining with an aqueous ion of hydroxide, forming the molecular compound of water. Water was our driving force in this acid-base reaction. All of the coefficients end up to be 1, so I'll just leave that as a balanced equation. We went from the molecular to the net ionic. Let me go down and model acetic acid with potassium hydroxide, because it will be different since we have the weak electrolyte. Acetic acid, HC2H3O2, is indeed aqueous, and potassium hydroxide, KOH, again is aqueous. Pattern of chemistry says H goes to OH. We will indeed form molecular water with an L, liquid water. So I do know that water is my driving force. And the salt that we form is potassium acetate, KC2H3O2, aqueous. Now remember, we labeled acetic acid as a weak electrolyte. KOH was strong. Water is a non-electrolyte, and potassium acetate is a strong water-soluble salt. We only break apart the strong. Weaks we leave together. Break apart, leave together, break apart. Let me repeat that. Leave together, break apart. Leave together, break apart. Up above we had two spectators. We had the aqueous ion of chloride and we had the aqueous ion of potassium. Two spectators in that particular equation. In letter B, I'm only seeing one spectator. I do not break apart the acetic acid. I leave it together. So for the net ionic equation, I leave together that weak acid. But I do break apart KOH, and I will break apart KC2H3O2. The aqueous ions of potassium are indeed a spectator ion, so I'm going to eliminate that from my complete to my net ionic. So for my base, all that's left is the aqueous ion of hydroxide. K positives remain aqueous in both. They mean in their dissociated form, so K's are going to be eliminated. That are the spectator. Leave together molecular water. It is in liquid. And break apart the potassium acetate. We've eliminated the acetate, so all that's left is the aqueous ion of acetate. Here is my balanced net ionic equation for letter B. Acetic acid, leave together. KOH, we broke apart. Water, leave together. Potassium acetate. We broke apart, eliminated the spectator ion of the potassium, and wrote out our net ionic equation. Let me model sulfuric acid and potassium hydroxide. Sulfuric acid is a strong electrolyte. It will dissociate in water. KOH, aqueous, forming a water molecule, and the salt of potassium sulfate. This one will need balancing. 2 Ks, 2 Ks, 2 H's, 2 H's, 2 OH's. We need 2 waters. Water, of course, has an L for a liquid adjective. K2SO4 is aqueous. What about spectators? H2SO4 is a strong electrolyte. Break it apart. KOH, a strong electrolyte. Breaks apart. Water is a non-electrolyte. It's molecule. Leave it together. Potassium sulfate is a water-soluble salt, strong electrolyte. It'll break apart. Here are your 2 spectators from letter D. The potassium ion and the sulfate ion will both be spectators. So 2 of them when water is our driving force. Very similar to how we had strong and strong, hydrochloric and sulfuric, both negative and positives ended up to be spectators. So we have a pattern of change for the net ionic equation showing the molecular water as our driving force. Notice I've reduced those coefficients to the simplest ratio. 2 aqueous ions of hydrogen, 2 aqueous ions of hydroxide made 2 water molecules. So I reduced that all down to 1 to 1 to 1 ratio. I'm going to jump over a little bit and I'll model, leaving these two columns for your work. Let me model some of the salt, sodium hydrogen carbonate. To do that, I'll have to flip to the letter J to make sure I'm writing on the correct form. So what I'll do is just bring this over and find the letter J as I write out sodium hydrogen carbonate with hydrochloric acid. Let me just scoot that up to find the correct spot. Over here, letter J. Hydrochloric, HCl. Sodium hydrogen carbonate, NaHCO3. Now with this pattern of change, we have a double displacement where HCO3 combine, HCO3, I'll combine to be H2CO3, and Na goes to Cl. Now remember, this is part 1. We do a double replacement, but we follow that with the decomposition of hydrogen carbonate to show the driving force. So out comes bubbles of carbon dioxide and molecular water. Carbon dioxide is our driving force overbearing the water. Since this is an acid with a salt, water is not the driving force. The evidence of change would be the bubbling. So for letter J, we would see gas bubbles. As a matter of fact, carbon dioxide is always going to come out as we start considering the carbonate polyatomic ion. I'll predict CO2 bubbles all the way down in that particular column. Now what about spectators? HCl, we said, was a strong electrolyte. We'll break it apart. Sodium hydrogen carbonate is a strong electrolyte. It will break apart. It is a water-soluble salt. H2CO3 is gone. Remember, it decomposed, so there's 3 products here. We have CO2 gas. It's a non-electrolyte. It's a molecular compound. Leave it together. We have liquid water, a non-electrolyte. Leave it together. But here, the third product is sodium chloride, a strong electrolyte, water-soluble salt, so it will indeed dissociate. Do we see any spectators? Well, I do. I hope you do as well. Cl and Na, I'll write those to the side. Na and Cl, dissociated over here, dissociated over here. They will indeed end up to be eliminated. Na and Cl both are dissociated. And friends, feel free to take the time to write out the complete ionic, but we're working towards seeing anything dissociated from the left to the right and just saving all that writing to move directly from the molecular equation to the net ionic equation. We'll eliminate aqueous ions of chloride. They're both dissociated forms. And we'll eliminate the aqueous ion of sodium since they're both in the dissociated form. And what do we find? We have an aqueous ion of hydrogen, an aqueous ion of bicarbonate or hydrogen carbonate, forming the products. CO2 is a gas and water as a liquid. Gas is our driving force. Molecular water is also formed. H positive aqueous plus HCO3 negative aqueous, forming carbon dioxide gas bubbles, some water left in the liquid form. Shall we do letter K, because it is a little bit different? And you probably have plenty of room on your paper, but I'm going to write bigger just so that the video is easier to see. So for letter K, I'm just going to put it on a separate sheet so I'm able to write large. Letter K, we have a weak acid, HC2H3O2, aqueous. We have that with a salt, sodium hydrogen carbonate. Now the pattern of change, H goes to HCO3 and Na goes to acetate. So we do our double displacement first, but we know that this follows a decomposition, that H2CO3 really decomposes to give us carbon dioxide gas and liquid water. So that pattern of change, double displacement followed by a decomposition. HCO3, I write that as carbonic acid and then decompose to see the gas bubbles. Sodium acetate is left as the salt after this neutralization. It is indeed a strong electrolyte. Now remember, we only break apart the strong, so letter K is a weak acid. Sodium bicarbonate is a strong electrolyte, water-soluble salt. CO2 is a non-electrolyte. It's a molecular gas. Leave it together. Water is a non-electrolyte. It's a molecular compound. Leave it together. But sodium acetate is a strong electrolyte. It's a water-soluble salt, so break it apart. Leave together, break apart. Leave together, break apart. So what are our spectators? I see just one. Do you see it? It's a sodium ion, isn't it? Sodium is a strong electrolyte appearing on both the left and the right side. It's the only one that does that. So when I move from my molecular to my net ionic, I'm going to get rid of my spectator, the sodium ion. Leave together the weak acid H, C2, H3, O2. Breaking apart sodium bicarbonate but eliminating the spectator, we get an aqueous ion of HCO3, -1. Aqueous ion of bicarbonate with a weak aqueous acid called acetic acid. Our driving force, the formation of the molecular compound of CO2, carbon dioxide gas. We have a liquid water molecule that formed, and eliminating from the strong electrolyte, that sodium ion that was our spectator, we're left with an aqueous ion of acetate. Moving from the complete to the net ionic, eliminating just one spectator in this example, Na+. Let me model from the far column as well. We're doing great work together. I want to make sure you have plenty of examples to kind of complete this correctly. We have the far column using sodium sulfide. And this one will be letter M, so make sure that on your paper you're finding the correct place, letter M over here. But I'm going to choose to write it big, so I'm just going to give myself plenty of room, putting a clean sheet here. So this is for letter M. Letter M has us taking a strong acid, HCl, aqueous, with a salt, sodium sulfide, Na2S. It's a water-soluble salt. Alkali metals are always soluble. Let's do our double displacement. H goes to S. Remember to consider charges. We have a +1 hydrogen, -2 sulfide, so H2S, aqueous. No, it's not. It's a gas. Sorry. This is the whole purpose of modeling. This is that rotten egg smell that we talked about in our NOPAC lesson. H2S, when it forms, is a molecular compound that comes out with a strong rotten egg smell, strong odor. H2S is a molecule, not an acid, because it comes out of water. Acids only exist in water. So hydrogen sulfide is how I would name this, because it's not dissolved in water. So technically not an acid, even though it starts with an H. It's not an acid because it bubbles out and gives that strong odor. And Na goes to Cl, so we have a water-soluble salt, Aq. This will need balancing. 2 H's, 2 H's, 2 Cl's, 2 Na's, 1 S. So I've repaired it. So let me just read it so it's a little bit messy. Sorry. 2 HCl, strong electrolyte, so it will break apart. It's aqueous. Plus 1 unit of Na2S, which is a water-soluble salt, so it is a strong electrolyte. It will break apart. A molecular compound, H2S, is a gas. That's a little g. There's our driving force, a rotten egg odor of hydrogen sulfide gas, and 2 units of aqueous sodium chloride. So I'm noticing that I have strong electrolytes on the left side. Chlorides and sodiums end up to be the spectators. So when we move from the molecular to the net ionic, we'll eliminate the sodium and the chlorides. So we end up with 2 aqueous ions of hydrogen combining with an aqueous ion of the sulfide, forming the gas hydrogen sulfide. And there's our net ionic for letter M. That will be the same pattern all through that same column. So we'll have 3 columns where water is the driving force and 2 columns where gas is the driving force. Your task now is to complete for every one of the boxes. I've done just a few examples. You have all of calcium hydroxide, all of sodium hydroxide, and to complete the letters we didn't do over here for the salts where gas is the driving force. This completed page will be due next time we meet to be turned in and scored.